In this video, I will define the energy and power of a discrete time signal, similar to what we did in the last two videos where we described the energy and power of continuous time signals. Let's start with an example. Let's say x of n is a discrete time signal that's drawn here. The energy of the signal x of n, we will define this to be the sum of the square of the absolute value, the magnitude of x of n as n goes from negative infinity to positive infinity. And just like what we did for continuous time signals, we'll define the average power in x of n by taking a window from time negative n to positive n, taking the average energy within this window and taking the limit as capital N goes to infinity, or the length of the window goes to infinity. So the energy within this window is given by the sum from negative n to positive n of the magnitude of x of n squared. Now the average energy within that window is given by this energy divided by the total number of samples we had within that time interval. And notice that when you observe for discrete time signals, if you observe the signal from time negative n to positive n, there are 2n plus 1 samples, including that sample at 0. And then we will take the limit of this as capital N goes to infinity. We'll call this as the power associated with the signal x of n. So you might remember the definitions for continuous time signals, and this look very similar to that, except that this 2n plus 1, which is an artifact of the fact that our time goes in discrete steps when we consider discrete time signals. Okay. Now, when I started defining the energy and power of a signal, we really use this idea of x of t being a voltage waveform, and we thought of the power dissipated across a 1 ohm resistor, so on and so forth. But then later on I said that even though we may have, that's a good way to motivate the definition of energy, we are actually interested in talking about the energy of signals which are not necessarily voltage waveforms. Now, a discrete time signal is typically not a voltage waveform. This signal here could represent anything. It could represent something that's not a physical quantity. So for example, we might be interested in a discrete time signal, which could be how the price of a stock or price changes as a function of days, for example, right? So we should really think of the energy of a signal as a measure of how big this signal is, or how large this signal is as a magnitude of the signal. Now, if you look at this definition of energy, you will notice that this is actually a very familiar quantity. If you think of x as a vector, if we think of x as a vector, with components given by x of n, then you can see that our definition of energy actually gives you the square of the length of this vector, right? That's a much more intuitively pleasing quantity to think about how large a signal is. So our definition of E sub x is nothing but the square of the length or magnitude of the vector x. In mathematics, this is also called as the norm of x, more particular, or the square of the norm of x. More specifically, Ex is the square of the 2 norm or Euclidean norm of of the vector x. And this is important because I think when you deal with discrete time signals and even continuous time signals actually, it is becoming increasingly important to take a linear algebra viewpoint to these signals. There is a lot of interesting results in linear algebra that can be used to analyze signals, and it's nice to make this connection between the energy, typically between what we do in signal processing and linear algebra. And this is one such a connection. What we define as energy is actually nothing but the square of the norm.